Hi everyone, my name is Ruby Barahona, and today I'll be presenting my honours thesis titled Classifying Dorsal V3 to Understand Variability in the Visual Cortex. Special thanks to co-authors Fernanda L. Ribeiro, Noah C. Benson, and Mark M. Shearer. So the early visual cortex is traditionally viewed as mirror-symmetric across hemispheres, following a canonical model, where V1 represents the full contralateral visual hemifield, and V2 and V3 represent quarter field representations. It is widely supported that the horizontal meridian, which is this line here, divides V2 and V3 into dorsal and ventral components. Shearer and colleagues in 2009 completed this canonical model, proposing the early visual cortex converges towards a center point known as the foveal confluence. However, this model has been challenged, with studies identifying individual variability and hemispheric asymmetry, particularly in dorsal V3. Ribeiro and colleagues in 2023 highlighted greater variability in the left hemisphere, significant dorsal V3 deviations, and a pattern discontinuity in dorsal V2 and V3 in some participants, featuring a Y-shaped lower vertical representation. So this image here shows polar angle maps of two participants' left hemisphere from the Human Connectome project. The left map indicates a canonical structure, whilst the right corresponds to a dorsal Y-shaped lower vertical representation, which is circled in black. However, the automatic classification method had limitations. Shown here is an example of maps that were misclassified into clusters by the automatic clustering algorithm. So the top row shows the average cluster maps for each cluster. The middle row represents maps that match the average for each cluster. And the bottom row showed maps that were misclassified by the automatic clustering algorithm. So for example, the polar angle map classified into cluster 1 here aligns more accurately with the early visual cortex organization in cluster 2. So to address this, we manually classified retinotopic maps to extend the work by Ribeiro and colleagues. We also explored heritability and handedness effects on variability. Using the Human Connectome Project retinotopy dataset, the high-resolution 7 Tesla retinotopy data were visualized using Connectome Workbench, and maps were classified into 5 clusters: canonical, similar to canonical, incomplete dorsal, no structure, and Y-shape. Expert reviews, polar angle gradient, and visual field sign analyses verified classifications. So the image on the left shows 5 participants' polar angle maps of the left hemisphere for each cluster. The black broken lines indicate vertical and horizontal meridians. The complete classification list is documented in a GitHub repository. So key findings included significant interhemispheric asymmetry, with Y-shapes more frequent in the left hemisphere and canonical patterns more common in the right. A linear regression showed no link between handedness and asymmetry. A moderate heritability estimate was found for left hemisphere Y-shapes, suggesting genetic contributions, but with substantial uncertainty. So the findings from this study revealed manually classifying and clustering each participant individually into 5 clusters based on pattern variability provided a useful assessment of variability. These results support substantial variability in the early visual cortex, particularly in dorsal V3 and the left hemisphere. Furthermore, significant variability between subjects examined, despite consistent methodology, explains why comparisons across species and methodologies has proven difficult in the past. An unexpected but important result of this study was the absence of an effect of handedness on hemispheric asymmetry. It appears interhemispheric variability stems from structure-related variation rather than functional dominance. However, the explanation for this leftward bias hemispheric asymmetry is not straightforward, with additional exploration into a more consistent source of hemispheric asymmetry needed. Future research would benefit from comparison with another large dataset, such as the New York University retinotopy dataset. This would provide a reliable comparison to the Human Connectome Project retinotopy dataset, allowing for a deeper exploration of early visual cortex variability across humans. Thank you for listening. If there are any questions, feel free to send me an email and I'll happily respond.